So, the recursive descent parsing technique that you are discussing, so there are some problems. The first problem is that the general recursive descent parsing, so this requires backtracking. So, the point is that as I said that there may be alternatives. So, suppose I have got two alternatives, A producing alpha is an alternative and beta is another alternative. So, first I will try with this rule, A producing alpha. Now, while doing this, so the input that we have, so input pointer was say, so this is my input sequence and the pointer was somewhere here when I started the procedure for A. Now, while trying out this alternative alpha, this input pointer has advanced to some extent. So, it has gone to this, and then suppose we find that no, A producing alpha is not the correct option to try out. So, it does not derive the final string. So, we need to come back and try the next alternative, A producing beta. But how do we do this? Because by this time the lexicon analyzer, so it has advanced its input pointer already to this point. So, it has to be taken back to this point before we start this A producing beta alternative. So, this is difficult because we have to take back the input pointer to come back to this point. So, that is what we are telling it here, that the last code that we have seen for the procedure A, so that needs to be modified to allow backtracking. In general form, it cannot choose an appropriate production easily, because we may have this left recursion, left factoring and all. So, it may be a left recursive grammar or it may require left factoring. So, if those are not done, then I cannot make a top down parser strategy, recursive descent parsing strategy using that grammar. So, we cannot choose an appropriate option very easily, whether to try out alpha or beta. So, there is no immediate guideline. So, even if this left factoring and left recursion elimination has been done, still it may be difficult to make a wise choice between alpha and beta. So, only when alpha fail, so we try out beta. So, exhaustively all the alternatives may have to be tried out. So, we need to try all alternatives. If one fails, the input pointer needs to be reset and another alternative has to be tried. So, this I have just discussed. So, you need to take back the input pointer for the lexicon analysis tool to the point from where we had started the procedure A. So, this is another issue, and the recursive descent parsers, they cannot be used for left recursive grammar. So, if the grammar has got left recursion, then we cannot use this recursive descent parsing. So, we will see some solutions to these strategies, these drawbacks in our next slides, but before that we take an example. Suppose we have got a set of production rules, S producing C A D and A producing A B or A. So, you see that we do not have any left recursion here, because here it starts with a terminal symbol C, here also it starts with a terminal symbol A. So, there is no left recursion. Similarly, there is no left factoring is also required, because we do not have any non-terminal big coming on the right hand side. So, it is not that I have got this A then something, so that we can take out A and like that. Suppose the input that we have is C A D. So, the way it proceeds, it first starts with first try out starts with the start symbol of the grammar, and I do not have any option here, there is only one rule C A D. So, it expands it by C A D. Then it tries out the first alternative S producing A B. So, if it does this S producing A B, then you see that it has derived the string C A B D, which is not C A D. So, it cannot be converted to C A D. So, it will fail the parser when it does this. So, it cannot go to the input string C A D. So, it will not match. So, it will, when the procedure for A is called, it will first call when the procedure for S is called. So, the procedure S is something like this. So, consume C. So, it is consume C, then it will call procedure A, then it will be consume D. It will be something like this, and the procedure for A is something like this. There are two alternatives. First alternative is consume A, and then consume B. So, this is one alternative, and the other alternative that we have is consume A. This is the second alternative. So, first it will try out the first alternative for A. So, this will be successful, because when it is CAD, initially the input pointer is here. So, procedure for S is called. So, it will consume C. So, input pointer will advance, it will come to A. Now, it calls the procedure A. So, it comes here, consumes A, and then pointer is advanced. So, it tries to consume B, but it finds that there is a D there. So, there is a mismatch. So, it understands that this alternative is not valid for this particular derivation. So, input pointer is taken back by one position from where this procedure A was called, and then it will find the other alternative says consume A. So, input pointer will be advanced, and then A part is done. So, it will come back to this point, and now it will say consume D from the procedure A. So, this will be consumed. So, that will be the third thing, and then so it can proceed like that. So, it fails at this point. So, it tries out the other alternative, A producing A and giving CAD. So, this way this recursive descent parsing works, but sometimes we do not like this type of backtracking, because then we have got the difficulty, because we have to see like how much has to be taken back and all. So, this predictive parsing, so this is a recursive descent parsing that needs no backtracking. So, it will be a recursive descent parsing only, but without any backtracking. Suppose I have got a rule A producing A1, A2, An. So, if the non-terminal to be expanded next is A, then the choice of the rule is made on the basis of the current input symbol. So, if we have got a number of suppose these are the alternatives A1, A2, An. So, these are the alternatives. So, which alternative to follow? So, based on the current input symbol, so it will take a decision. Okay. So, if we can take the decision properly, then we can make a predictive parser for the grammar. So, if we cannot make a decision for all the productions, then predictive parser design for that particular grammar is not possible. So, in many cases it will be possible, and in many cases it will not be possible. So, we will see the situations for both. So, procedure for technique for designing this non-recursive version or predictive parsing mechanism is to make a transition diagram for every rule of the grammar, like DFA or NFA, deterministic finite automata, non-deterministic finite automata. So, we make a transition diagram, and then we try to optimize the transition diagrams by reducing number of states, yielding the final set of diagrams. So, we first draw a set of diagrams based on some optimization of the diagram. So, we come to the final stage of diagram. Whenever we are trying to parse a string, we simulate the string on the transition diagram. So, as if we are making transitions through the transition diagram using the inputs from the string. If we have consumed the input transition, after consuming the input, when we are consuming the entire input, if the transition diagram reaches an accept state, then it is taken as parsed. Okay. So, if we transition diagram like DFA and NFA, it will have some initial state and a set of final states. So, if it reaches one of the final states after consuming all the inputs, then we will say that the parser has accepted the input. So, we will take some example. So, suppose we have again take that expression grammar E producing E plus T or T, T producing T star F or F, F producing within bracket E or I D. Then after removing this left recursion and left factoring, the rules will be something like this: E producing T, T dash, then T dash producing plus T, T dash or epsilon, F producing T producing F T double dash, and T producing star F T double dash epsilon, and then T producing within bracket E I D. Now, so this is the for the first one. So, we have got a diagram like this. E, this is for E. So, produces it uses T and T dash. Okay. So, on getting these two symbols, so it will come to a final state. Similarly, T dash, so this is red is a final state. So, on getting epsilon, so it can come to final state, or it can be so so this is our T. So, this is F T double dash, then this is T dash. So, T dash is actually this is something wrong. So, this should be plus, this should be T, and this should be T dash, and then this T dash, this is F T double dash, then this T dash producing so actually this should be T double dash. So, this is T double dash producing so this should be T double dash producing a star F T double dash or epsilon, and then this this should be F producing within bracket E or I D. So, this is for F within bracket E or I D. So, this is T dash. So, this should be plus, this should be T, and this is T dash, then T producing F T double dash, that is all right. Then this is for T double dash producing epsilon and star, this should be star F T double dash, and F producing within bracket E and I D. So, this is the final set of transition diagrams that we can have, and then so we can do some optimizations, like starting with the start symbol. So, on getting T, it comes to this state, and so this is the rule for this is the rule for T. So, the T is again coming back. So, coming back to the start state. So, if there is no expression after this, so it can come to the final state, or if there is a plus symbol, so it can come to this. Similarly, if for this F, it can come to on getting epsilon, it can come here, but if it gets F, so it can come to this state, and getting star, it can come back to this point, and again proceed on epsilon to the next state. So, this can be done. So, how do we simulate it? We start with the start symbol of the set of diagrams. Start with the start state, and if it is a terminal, we consume it and move to the next state. If it is a non-terminal, so we go to the state of the DFA of the non-terminal and return on reaching the final state. When we return the final state of that non-terminal transition diagram, we return to the start state, and we return to the original DFA and continue parsing. So, this way whenever we reach any final state, so we come back to the original DFA and continue parsing. On completion of input, when the input has been seen completely, so if we find that we have reached a final state, then the string is successfully parsed. So, otherwise it is not. So, the problem that we have is that inherently it is a recursive parser. So, it consumes lot of memory as the stack grows. So, we are calling the routines again and again. So, as a result we are doing it by means of transition diagram, but it is taking lot of time. It may take lot of time because of this recursive nature. And to remove this recursion, we can use one type of parser which is known as LL parser, which will use a table for the lookup procedure. So, this LL, so these two L's stand for, the first L stands for leftmost derivation, and this is stands for left to right scan of the input. This will do a left to right scan and it will produce a leftmost derivation for the parse tree. So, we will see how it can be designed, but to come to that, so we need to have some definition. One is known as first set, another is known as follow set. So, these two definitions we have to learn by heart, because many times in our compiler codes, so we will come to these two sets, first and follow, and we should be able to compute them very confidently, and particularly this follow set computation is slightly tricky. So, we have to be careful there. Okay, let us try to understand what does it mean. So, first of alpha is a set of terminals that begins strings derived from alpha. As you know that alpha is any string of terminals and non-terminals. So, if it is whatever be the string, so from starting with this alpha, whatever string of whatever strings you can derive. Okay. So, in that whichever symbol appears as the first symbol. So, that is that particular terminal symbol. So, will be included in the first set. So, if alpha in 1 or 0 or more derivations gives epsilon, then epsilon is also in the first of alpha. Okay. Now, if I have got so how is it going to help? It is going to help because if I have got two productions, A producing alpha and A producing beta, and at present suppose I am looking in the current input symbol is A. So, based on this we will be able to take a decision like which rule to follow. So, we look into the two sets, first of alpha and first of beta. Now, if the symbol A belongs to the set first of alpha and A does not belong to first of beta. So, in that case there is no point trying out the A producing beta alternative for this particular string. So, we should try with A producing alpha type of rule. So, this way it will be helping us in predicting like which rule to follow. So, in predictive parsing, whenever we have got A producing alpha or beta, if first of alpha and first of beta are disjoint sets, then we can select appropriate A production by looking at the next input. Okay. So, this way it is going to help. Another definition is follow of A. So, where A is a non-terminal symbol. So, follow of A is a set of terminals A that can appear immediately after A in some sentential form. So, sentential form means anything that you can derive with the start symbol of the grammar. Suppose S is the start symbol of the grammar and you are applying some rules, and so ultimately this rule leads to the set of terminals. So, this is the final input string. Now, all these intermediary things that you have, so they will be called sentential forms, because they are actually derivable from S and will lead finally to some string of the language. So, any string of any stream of symbols, terminals and non-terminals that can finally lead to some input string involving terminals only, and this string this is derivable from the start symbol of the grammar, then that mix of mixed string of terminals and non-terminals. So, they will be called it will be called a sentential form. So, and in that sentential form, suppose I have got a sentential form here I have got the symbol A, and after that suppose this small a character the terminal small a appears, then we say that small a belongs to the follow of A. In another sentential form, maybe this A is followed by B. So, B is also in the follow set of A. So, A can be followed by A or B. So, the follow set of A will have these two symbols A, B, some more may be there, but these two must be there. So, if we have starting with S in 0 or more derivation steps. So, if you come to this type of sentential form alpha A A beta, and for some alpha beta, then A is in follow of A. So, this particular small a is in follow of capital A. If A can be the rightmost symbol in some sentential form, then dollar is in the follow of A. So, if you start with A S and see that you can derive something, so that A is the last symbol of that sentential form, then it is assumed that this may be followed by the dollar symbol. So, and dollar matches with the end of string. So, whenever we have got a string, so the end of string is marked by the dollar symbol. So, that is a convention followed by this compiler designers. So, it assumes that the last symbol of the input is the end of string symbol, which is dollar. So, if this A happens to be the last symbol of any sentential form, then this dollar will also be in the follow of A. So, these are the definitions of first and follow. First is any string that can be derived from alpha, whatever can come in the first, whatever terminal symbol can come at the beginning. So, that is the first of A alpha. Follow means you take any derivations from the start symbol of the grammar, and all the intermediary derivations, in all the intermediary derivations, if this any non-terminal A can be followed by another terminal symbol small a, then the small a is going to be in the follow set of capital A. So, that is how this first and follow are defined. Now, how is it going to help us? So, before going to that, so let us see how can we compute this first set and follow set. For computation of the first set, we apply the rules until no more terminals or epsilon can be added to any of the first set. What is the rule? So, if x is a terminal symbol, so we are trying to compute the first of x, where x is a grammar symbol, it can be a terminal, it can be a non-terminal. So, if x is a terminal, then first of x is definitely the x itself, because nothing more can be derived from a terminal symbol. So, that is there in the first of x. If x is a non-terminal symbol and x producing y1, y2, yk is a production for some k greater or equal 1, then we place a in first of x if for some I a is in first of yi and epsilon is in all of first of y1 first of up to first of yi minus 1, that is y1 y up to yi minus 1, they produce epsilon. So, let us try to explain this part. So, what it says, suppose I have got the x is a non-terminal symbol and we have got a rule which says it is y1, y2, yk. So, anything that you derive from x, suppose this from this y1 I can get a derivation like a alpha, then y2, etc. This y1 can be expanded to a alpha, then definitely a is there in the first of x. So, that is what the first part says, if y1 whatever is there in the first of y1 will be in the first of x. Okay. So, if we just take I equal to 1, then so this whatever is in first of y1 will be in first of x. Other so what about the terminals belonging to the first of y2? So, I will have this thing if y1 can give me epsilon. So, if y1 can be reduced to epsilon, then so I had got this y1, y2, y3. Now, if this y1 can be reduced to epsilon, then after some time I am getting the configuration like y2, y3, provided y1 can be reduced to epsilon by means of some steps. Okay. So, then this whatever is in first of y2 will also be in first of x, provided y1 can give me epsilon. So, in general, so if I have got say x producing y1, y2, yi minus 1, yi plus 1 up to yk, then whatever is in first of yi will come to the first of x, provided each one of them can give me epsilon. That is, first of all of them, first of y1, y2 up to yi minus 1, all of them have got epsilon in them, or I can say that is this y1, y2 up to yi minus 1 can give me epsilon. So, this is the second rule, and it says that if x producing epsilon is a production, then we add epsilon also to the first of x. So, that is if there is a production rule x producing epsilon, then it will come. So, let us see how this first can be computed. So, this is say this is a set of grammar rules, E producing T dash, E dash producing plus T dash or epsilon, T producing F T dash producing star F T dash or epsilon, F producing within bracket E or I D. For some of the rules, so the first rule says that whatever is in first of T will be in first of E, and if T can give me epsilon, then whatever is in first of E dash will also be in first of E. Now, T does not give me epsilon, so naturally I do not have that liberty. So, whatever is in first of T will be in first of E. Now, what is in first of T? First of T is equal to first of F, okay, because by this rule you see that first of T is equal to first of F. And what is first of F? So, this rule will tell that open parenthesis is in first of F and ID is also in the first of F. So, first of F has got open parenthesis and ID, and from this rule it says that whatever is in first of F is in first of T. So, first of T also has got open parenthesis and ID. And what about first of E? First of E, by this rule it says that whatever is in first of T is in first of E. First of T is open parenthesis ID. So, first of E will also have open parenthesis and ID. Now, first of E dash, from this rule you see it is plus T E dash. So, it starts with a terminal symbol. So, it cannot have anything else. So, this plus is in first of E dash, and E dash producing epsilon is a rule. So, epsilon is also in the first of E dash. So, E dash so first of E dash has got plus and epsilon, and finally, this T dash it can give me star and epsilon, because this can give me star and this is epsilon. So, star and epsilon can come. So, in this way we can compute the first set for the grammar rules that we have here.